Hi folks, in this video I'm going to talk about binary numbers and basic operations with them. The reason we need to know about binary numbers and at least how a computer operates with them, does basic operations on them, is that all the information you have stored on the computer and the information that is being transferred between different components of the computer or different computers is actually represented by binary numbers. So binary number is a number in a binary numeral system or base 2 numeral system, which is a positional expression of numbers with radix 2. So base and radix are synonyms, and they denote the number of unique digits or symbols used in the system. So the standard base 10 or decimal numeral system has radix 10, which means we have 10 unique digits, 0 to 9. And similarly, in binary system, we have only 2 digits, 0 and 1. So all the numbers are denoted by these 2 digits only. And the same way the decimal numbers have these positional values for each digit, that same logic works for binary numbers. So let's take an example like 1509. So we write 1509, and every single digit in this number represents a value equal to the value of the digit multiplied by the base or radix to the power of the index of the position. So more precisely, in case of 1509, we can say it's equal to 1 times 10 to the power of 3 plus 5 times 10 to the power of 2 plus 0 times 10 to the power of 1, and then finally plus 9 times 10 to the power of 0. So in binary system, every number, as I said, has only ones and zeros. So let's take the number which is written as 1101. And with similar logic, we can say that we can calculate the value of this number in decimal system. So the first one will be multiplied by the 2 to the power of 3, since we have only 4 digits and we start indexing with 0. So it will be 1 times 2 to the power of 3. The second one will be plus 1 times 2 to the power of 2. The third one is 0, so it's 0 times 2 to the power of 1. And finally, the last one is 1 again, and so it's 1 times 2 to the power of 0. If we sum this all up, we'll see that 1101 in base 2 system is actually 13 in base 10. So everything that works, all the operations between these numbers that work in our standard base 10 or decimal system, we can do in absolutely same logic, with absolutely same logic between binary numbers. But in computer systems, usually some of the operations are done differently for the purpose of being faster or saving some resources like power or number of logic gates that do the calculations. So in binary system, negative numbers are represented in different ways. It depends on the computer architecture, and we'll cover some of the cases or some of the options. And as I said, all the arithmetic operations between numbers are doing the same thing, but might do it in different ways. So we have addition, subtraction, multiplication, division. We can have fractions, we can have power or exponent, and so on. So, but binary system has its own unique to itself or not unique, but more commonly used operators. And those are, we have several binary operators. Binary means it takes two operands. So we have AND, OR, and XOR, or exclusive OR. And there are also unary operators, which take only one argument, and those are the NOT, right shift, left shift, and logical right shift. So let's just go through the definitions of these ones. These are really important. So AND, what it does, it takes two numbers, two binary numbers, and for each digit, so it assumes, not assumes, but the result of the operation is 1 if both the digits are 1. In all other cases, the resulting digit is 0. So when we are talking about the binary operators, we always define them per digit. So we calculate on the whole numbers, on an n-digit number or whatever digit number, but the definition is just by one digit because the logic is the same. You just apply the same logic on all positions, and you align, since it's binary, you need two numbers, you align these two numbers by the right position. So OR is defined as 1 for the positions where at least one of the numbers has 1. And if both have 0, then it's 0. So exclusive OR is gives you 1 only when just one of the numbers has 1 in that position. So if both are 0 or both are 1, it gives you 0. So those are the binary operators. So one thing I want to mention is in binary numbers, the positions are also called bits, and the rightmost position is called the least significant bit, and the leftmost position is called most significant bit. So in computer hardware, like how they are stored, there is no left or right, but usually it's how we represent or draw. So we always put the most significant bit on the left, similar to what we have in decimal numeral system. So the unary operators are not. So not is basically inverting the number. In all the positions that there are zeros, it turns them into 1, and the ones turn into 0. So the shift operators just shift the numbers, shift all the digits or the bits either to right or left, depending on the operator, and then the bits that carry over, so they are filled with either zeros. There is a special case for negative numbers. So usually the negative numbers are represented by the same positive number, plus they add one extra bit at the very front. So before the most significant bit, we add one extra digit, and if it's set to 1, it means it's negative. If it's set to 0, it means it's positive. So for negative numbers, when we shift to right, we don't replace all the extra carried over digits with zeros. We keep the first one as 1 to keep the sign. There's also logical shift, which clears the sign too, but we don't need that right now. So let's jump into some examples and see how these operators work on numbers, and make sure we understand everything. And it should be, once you understand how it works, it's really simple. It's similar to the standard decimal system that we use every day. So let's do some examples. All right, so let's do some examples. Let's take decimal 21. So I'll mark it decimal with denoting the base 10. Okay, so this basically in base 10 it's 2 times 10 to the power of 1 plus 1 times 10 to the power of 0. Okay, so to convert this to binary, we need to know what's the largest power of 2 that 21 contains. So it's 16, which is 2 to the power of 4. So we can say 1 times 2 to the power of 4 plus. So 16 plus 8 is over, so we don't have the 2 to the power of 3. So 16 plus 4 is 20, so we have it. So 1 times 2 to the power of 2, and then 20, we just need the 1. So 0 times 2 to the power of 1, and finally 1 times 2 to the power of 0. So in other words, if we just take the factors for each position, it's 1, 0, 1, 0, 1. So this is, so 21 in decimal is 10101 in binary. So similarly, let's say we have another number which is 13 in decimal, and then if we calculate the same way, we have 8 plus 4 plus 1. So it's 1 times 2 to the power of 3 plus, we need 4, so 1 times 2 to the power of 2, and then plus 1. So we have 1, 0, and then finally 1 times, and this, if we write the factors, it's 1, 1, 0, 1 in binary. And then let's take one more number, which is 28 in 10. So if we see which powers of 2 we have, it's 16, which is 2 to the power of 4. Then we have 8, so that's 24, so 2, 3, and then we have 24 plus 4, and that's it. So we don't have the, we don't have the 2, and we don't have the 1. And finally it's 1, 1, 1, 0, 0. Okay, so now let's do some, for instance, addition. So if we do 21 plus 13 in decimal, we just do, if we put on sum under one under other, so we take the first digits, 4, 3. So similarly, if we write this down in binary, 1, 0, 1, 0, 1, and 13 was 1, 1, 0, 1. So note that we should always align by the least significant bit. And here, missing 1 is basically 0. We can just add the 0. And 1, 1. So since there is no 2 in binary, we need to make it 0 and carry the 1 over to the next digit position. So 0, 0, but then we carried over 1, so there is 1 here. This is the same thing, 0, and then 1 we carry over here, so 1, 1, again 0, 1 we carry over 1, 1, again 0, and 1. So if we try to translate this, so this is position 0, 1, 2, 3, 4, 5. So this is in binary, and this equals to 2/5 and 2 to the power of 1, which is 34. So everything looks good so far. So similarly, if we do subtraction, let's see. So if we do 21 minus 13. So let's do this. 1, 0, 1, 0, 1. And then we have 0, 1, 1, 0, 1. So 1 minus 1, 0, 0 minus 1, 0, 1. So here we do the same thing as we would do for decimal. So since we cannot subtract 1 from 0, we borrow from this next position. So it would be 10, but here it's basically 2. 2 minus 1, it's 1. And this was 0. 0 minus 0, we don't need to write the most significant 0. So this makes it 0, 1, 2, 3, so 8. Because we have only 1 in the 4th position, which is the 3rd. So 2 to the power of 3, right? 8. So everything works so far. So for negative numbers, let's try. Since I said it's a little different, and let's try this. So let's try to subtract 21 minus 28. So in decimal, this would be minus 7, basically. Which one way to do this is basically find the bigger number and then subtract the smaller number from the larger number and then put the correct sign. So it's minus 7 here. So for binary, we can do the same thing. We can either subtract the smaller number from the bigger and then add the restore the sign. And that's one way to do it. That's easier. But most of the computers won't do that. So what would happen is the processor would use one of the bitwise operators to convert the subtrahend into a different number and then sum them up. So it's basically doing, so instead of doing a minus b, let's see, a, okay, I don't know why this is not working, a, let's try here. So instead of doing a minus b, it would do a plus minus b. So to get minus b, we can use the negation. So we can do a plus not b and plus 1. This would give us the negative b. So in this case, let's see. So we want to negate this one, 1, 1, 1, 0, 0, which is 28. So as I said, negation is we just invert the digits. So it would be all the ones will become zeros, and then the zeros would become 1. So this is basically 1 plus 2, so 3 in decimal. And then we need to add 1. So instead of subtracting, instead of doing this, we can do, this is equivalent to 1, 0, 1, 0, 1, and then we do the inverted 0, 0, 0, 1, 1, and then we add 1 more. So all of this we need to add together. So let's do one by one. So first let's add this one to the bottom number, so it will be 1 plus 1. So let's do this, 1, 0, 1, 0, 1, plus, so if we add this would be 0, 1, carry over again, 0, carry over to next one, 1. Okay, so now we can add this 1, 0, 1, 1 is 0, 1 carried over to the next, and then 1. So if we calculate this, this is in decimal 1, or 1, 0, 1, 2, 3, 4. So 16 plus 8, 24, 25. 25. So this doesn't look like the right answer, because to restore the sign, we need to do something more. So it's basically if we subtract it. So we need to negate this again. I think we need to negate this one again, and then do the same operation again, basically. So if we negate this, we'll get 1, 1, 0, and then this would become 0, and then we need to do plus 1. So we do plus 1 because it's called the 2's complement, because we are taking the number and subtracting it from the smallest power of 2 that is larger than this number. So basically putting 1, so imagine here 1 at the index position previous to the most significant position of the given number, and then all zeros. So this will be a power of 2. And then we subtract this from this number. So that's why it's the same as negating and adding 1. And then we need to add 1 to this. So it will be 1, 1, 1, 1, 1, 1. And this is negative also. So it would have 1 in the very first sign. So this one usually is not really the 6th one in computer storage. It would be either 8. So we'll get to that in a future lesson. So this is basically minus, and then so third index is second order, so 2 to the power of 2 plus, no space here, so let's do this, 2 to the power of 1 plus 2 to the power of 0. So this becomes 7, minus 7. So 21 minus 28 is minus 7. So again, every single operation that you can do on the decimal numbers works here, and you can do it the same way. Division also, multiplication, you can do exactly the same way if you write them under one each other and then multiply. First, like let's say we have a 1, 1, 0, 1, and then 1, 1, 0. So you can multiply first the 0 with all the digits right here, and then shift 1 digit and then multiply this one, and then shift 1 digit, multiply this one, write them under each other, and then sum them up. You'll get the right answer. You can try that and convert to decimal. See that you got the right answer. So I think this gives you a good idea of how the operations work, and you can search on the internet if you're curious about what specific operation or how is it exactly implemented, how the processor handles it. You can look it up, but at least you now have idea of what are binary numbers, how they are represented, how the operations work, and I think it will be useful in the upcoming videos. So I think this is a good exercise